So welcome everyone to our Toronto AI in Robotics seminar. And today we are glad to have Sven Lilge to give a talk on tendon-driven parallel continuum robots. So Sven received a Bachelor of Science and a Master of Science degree in Electrical Engineering and Information Technology from the Leibniz University, Hanover, Germany in 2014 and 2016, respectively. From 2017 to 2019, he worked as a research assistant at the Laboratory for Continuum Robotics at the Leibniz University, Hanover. His PhD candidate with the Department of Computer Science and a research assistant with the Continuum Robotics Laboratory at the University of Toronto, Canada. His research is primarily concerned with parallel continuum robots, focusing on design, modeling, control, and kinematic evaluation. Sorry. So looking forward to your talk, Sven. Feel free to take over.
Excellent. Thanks so much for having me, and thanks for the introduction. Let me share my screen. All right, can you all see my slides? Okay, excellent. Yeah, thanks again for the invitation. I'm very happy to give this talk today, which is titled Tendon-Driven Parallel Continuum Robots, and which essentially presents a chunk of my PhD research that I've conducted so far. So yeah, second. Yeah, you already introduced me quite well, so we'll make this short, but I want to briefly say a couple words about myself so you kind of get to know me. I'm originally from Hanover in Germany, and that's also where I was for my bachelor's and my master's at the Leibniz University in Hanover. And I actually have both of my bachelor's and master's in electrical engineering, so I'm from an engineering background. And then in 2017, I joined Jessica Buckner-Kaas at her Continuum Robotics lab to kind of start my PhD and work as a research assistant. And then in 2019, when Jessica got an offer from U of T, I transitioned with her to U of T, where I'm right now, a PhD candidate in computer science. And I'm here since 3 years now, and hopefully graduating soon. Well, that's just about me. So I want to start my talk by introducing tendon-driven continuum robots to you. So I'm sure you're all familiar with how conventional robots look like. If we think about robots, we often see these robotic arms that are composed of these rigid links with these discrete joints connecting these links. But continuum robots are actually inherently different in their structure and in their characteristics. So you can see here in this video, the main material we use to actually construct these robots is like an elastic and compliant material. In this case, it's a specific nickel titanium alloy. And that makes the robot very flexible and compliant. So you can see here, it's very easy to just push around this robot with my own hand and deform it essentially. That's one of the main features of these robots. And the other is that because of this compliance and flexibility, I can actually deform and bend the robot in these complex shapes in 3D space. And I can basically follow these non-linear, curvilinear trajectories and conform to them. So rather than having a very discrete, rigid link joint structure, I have a smooth kind of shape in 3D space. And this shape here in this specific robot prototype, which is a tendon-driven robot, is actuated using tendons. So you can see here along this flexible material, we have several of these what we call spacer discs. And these spacer discs are used to basically route tendons throughout the whole structure of the robot. These tendons are then terminated at different points throughout the structure and then lead into this big actuation unit here at the back of the robot. And that's actually where all my actuation and my motors are localized. And these just pull and release these tendons that are routed through the robot. And by pulling and releasing them, I more or less induce bending moments at different locations along the robot shape, and then can actively control the deformation and bending of this robot. So one main advantage is that all of the motorization is back here in this unit. So I don't have any joints or any motors in the structure of this robot. So I can build it very, very small. And that allows me to have these robots with a very small diameter. So just to quickly summarize, the main characteristics of these robots are A, it's highly compliant and flexible. B, I can conform to these highly nonlinear shapes in 3D space and can potentially follow curvilinear paths. And then 3, this robot can be very small because all my actuation and motors are actually outside of the robot in an extra actuation unit, how we call it here in the back. So the combination of these three characteristics make the robot actually very predestined for specific applications. And yeah, the main applications that are motivated for this type of robot is any application that features a highly cluttered or constrained environment. And one example is shown here in this image. It's a mechanical inspection and repair tasks. And in this specific example, we can see the inside of an aircraft engine. So we can see the turbine with its individual blades. And one idea would be to like use these tendon-driven continuum robots to enter this turbine through like the borescope hole, and then navigate in this highly constrained and cluttered environment to reach different sites, inspecting these blades and potentially even repairing some damage that we find on these blades. So that's the task that's like right now done like manually with like manual borescopes, but this could potentially be using these robots. When we talk about this specific application, and particularly about potential repair tasks or any task actually where we need to apply manipulation forces to the environment, this is where we face one of the main open challenges in continuum robotics. And this is connected to their inherent compliance. So as you've seen before, the robot is very soft, and the softness and compliance might make it very difficult to actually apply forces to the environment. The robot just like lacks stiffness, and instead of manipulating the environment, the robot would rather like bend away itself in the worst case, and we're not able to actually do meaningful stuff in terms of manipulation, just because this force is not high enough. And one idea that comes to mind here now is to not only consider one continuum robot that enters this cluttered environment and manipulates the environment, but consider a second robot that through like another opening, for example, goes into the same workspace, and they're then coupled together to form a coupled, parallel, and more stiffer structure. So now with this increased stiffness, I might have the ability to actually apply higher forces to the environment, which might then enable some of the tasks that we actually envisioned for this robot, for example, repairing some damage that we found on the blades. So this parallel coupling of continuum robots, it's what we call parallel continuum robots. And this idea is not entirely new. There exists a broad range of literature on parallel continuum robots, and I just show some very prominent examples here. It's not exhaustive what I present here. So like some examples include some counterparts to conventional continuum robots that we know. So for example, a continuous counterpart to the very well-known Stewart Gov platform, or a continuum counterpart to the very well-known Delta robot. And some other examples like soft parallel robots or planar passive link parallel robots. So the idea of coupling continuous structures together parallelly is not new, but what you can see here in this specific context is that all of these robots more or less mimic very specific rigid link counterparts. And these links are often just like flexible links in the structure, and are not like full continuum robots themselves. And we want to kind of like take this concept of having these parallel continuum robots and apply it to the tendon-driven continuum robots that you've seen in the video before. So that leads to what we call tendon-driven parallel continuum robots, or short TDPCR. And you can see one example here. It's essentially a coupled structure of 3 individual tendon-driven continuum robots, and they are coupled to one common end effector. And because in our case, these individual links of this robot are fully actuated continuum robots themselves, we can actually have these scenarios where we can first control these robots individually, maybe approach an object from different directions, and then like grab it and manipulate it in like a coupled structure. So that's what makes this different than the large bulk of like the state of the art on parallel continuum robots. And yeah, that's essentially what my PhD is concerned with. So throughout my PhD, I am concerned with the design, the modeling, and then the evaluation of these novel structures. And throughout the following, I want to kind of briefly talk about all of these 3 aspects. So I want to start by just talking about the design of TDPCR, so like how we design the structures kinematically and mechanically. So we started this project actually a couple years back, and in the beginning we focused on like having simple structures that we can like easily describe to first understand what is happening for these specific manipulators. So what you can see here is like a very simple 3 degree of freedom planar manipulator that consists of 3 individual kinematic chains. And each of these kinematic chains or links has tendon actuated continuum robot segments that can bend with 1 degree of freedom. So this structure actually still mimics one of the conventional parallel robots, and we kind of substituted some of the rigid link actuation with tendon-driven continuum robots to first have like a first feasibility how these robots can be realized, or even what their characteristics are. And then more recently, we started to extend this whole concept to a spatial manipulator that can control its pose with like, the pose of the end effector fully with 6 degrees of freedom. So we got rid of the kind of like last rigid links that were in the structure. And like now every kinematic chain is just like a continuum robot on its own. And then they're still like they're coupled to this end effector here, which is a triangular platform. And now, unlike the robot on the left, this one can move in 3D space, and I can manipulate the end effector in all directions. And in today's talk, I want to focus on the design that we derived here on the right. And I want to just start by briefly explaining how this design kinematically kind of works. So here on the left, you can see a simple sketch of this design. We see the parallel assembly of three individual tendon-driven continuum robots, and they're all coupled to a common end effector using spherical joints. And then looking at the cross section of this robot, we can see that these spacer discs have 4 holes. So each robot can have 4 tendons rooted inside them. So what that allows basically is to, by pulling and releasing these tendons, I can bend the robot in 2 different directions. So the way that works is the tendons that are opposite of each other are always kind of actuated as a pair. So once I pull one tendon, I will release the tendon that's opposite by the same amount to basically bend the robot in the direction of the pulled tendon. So even though I have 4 tendons here, I can actuate them with 2 motors in total because I actuate these as tendon pairs, and then can have bending in 2 degrees of freedom. And as an additional actuation component for each of these individual tendon-driven continuum robots, we consider a translation of their base along their principal axis. So when I say principal axis for continuum robots, that just means it's like the axis where the length of the continuum robot kind of evolves along. So by translating the robot along this axis, we can enable kind of like an inserting motion. So if we consider a very cluttered environment, I can basically, by translating the robot into this environment, insert it there. So that means now we have 3 degrees of freedom in actuation for each of these robots. So in total, this is a 9 degree of freedom robot in actuation, which makes the robot actually redundant because our end effector pose will be controlled with 6 degrees of freedom, 3 for translation and 3 for orientation. So that's just briefly how this robot is designed. And one of the main questions that I asked myself during my PhD is, how can we now model this robot efficiently and also accurately? So that's kind of the next part I want to go into in more greater detail, which is concerned with the modeling of tendon-driven parallel continuum robots. So for this part, I first want to just introduce a couple of variables and parameters that we will need throughout the following. So I know this figure looks a bit loaded, but it's we can break it down together and then understand what each of these specific variables and parameters mean. So when we talk about modeling, what we're mostly interested in is what is the resulting end effector pose and shape of these continuum robots. So the end effector pose in our case is we attach kind of a frame to the center of the end effector platform, and then we can describe this frame by a transformation matrix with respect to some fixed frame S. And then this transformation matrix is a simple 4x4 matrix in the special Euclidean group, depicting orientation and position of this end effector. And then we also kind of want to know what is the resulting shape of each of these continuum robots, which we for now will say is the parameter X depicting the shape. So both of these parameters depend on a number of variables. One, of course, is my actuation variable. So basically what's the command I send to my actuators or motors, which is Q. So in our case, it's how much do I pull the tendons or how much do I translate the robot? And then another parameter that actually can influence the end effector pose and the shape is the external loads that are acting on the end effector. So if we actually envision this robot in one of these applications, it might interact with the environment, and there might be some interaction force, and that usually would then apply on the end effector of the robot. So that's a 6x1 vector. It's just a force in a moment, basically acting on this robot. So having all of these variables defined, what we want to do in like modeling is we want to derive equations that relate all of these variables with respect to each other. So we can actually derive, we want to derive equations that, let's say we know the actuation of the robot and we know the external force that's acting on the robot. We want to know the pose of the end-effector and the shape of each of the robots. So that's the very simple forward problem. I'm sure all of you have seen this in robotics here. Sorry, I just read the chat on the side. I will answer this question after this slide. Yeah, so again, we know Q and W, and then we want to know the resulting pose of the end-effector, and we want to know the shape of each robot. So that's basically the forward kinetostatic problem. We say kinetostatics because we're considering kinematics and statics. What's important to note here is the model that we will discuss today is purely static, so there's no dynamic behavior. And the same way we can define like the inverse problem of that. Let's say we know where the end-effector should end up, and then we can basically solve for the actuation values that will solve. We can solve for the actuation values so that the robot can be controlled towards that desired end-effector pose. And the chat in the question in the chat was if this paper is currently on archive, and no, it's not. Unfortunately, I'm sorry. All right, so before we can go into deriving these equations, one important thing that we need to think about is like, how do we actually represent the shape of this continuum robot? You've seen in the video that this robot basically can continuously bend along its whole structure with respect to the tendon forces or like any other external forces. So theoretically, this robot can have any shape, and I would need kind of like what we say infinite number of parameters to like truly and accurately depict the shape. But often it's like not really feasible. So there are like a couple approaches to kinematically represent the shape of this robot. And the next slide. So I just outlined the three most prominent approaches that you can find in the literature. So the first approach to represent the shape and the kinematics of a continuum robot is what we call the variable curvature representation. This is like actually the most general representation because it makes the least simplifications and assumptions. So basically we say that we can parameterize our continuum robot along its length with a one-dimensional parameter S. So think about the robot not just being a simple 3D line in space. And then for every point along S, which we call the arc length of the robot, we can define a completely new and independent curvature. So for every point along S, I can have any curvature, which then means for every point along S, I have like a specific position orientation describing the center line of this rod. So this is a completely continuous formulation. And there's at this point, like no approximation done. This is actually one, so that's like the main drawback, because I have like no approximation and simplifications here. This might be computationally expensive, but we will look at this later in more detail. So a second more simplifying approach is saying, okay, I can actually approximate the shape of my continuum robot by constant curvature arcs. So my shape is now represented by like a series of constant curvature arcs, and every constant curvature arc basically has one constant curvature or one radius and one bending angle in which this curvature happens. So I already have like for each arc only 2 or 3 if I also consider the length parameters to describe it. And then just by having a finite series of curvature arcs, I can heavily reduce like my parameter set to represent the shape. The main drawback here is that this representation might not be super accurate because in many cases, it's actually not super feasible to just assume constant curvature for the shape of the robot, especially if I have external forces acting on the robot. And then a last often used representation is just assuming like approximating the whole continuous shape like a pseudo-rigid body. So we kind of go back to, oh, well, what if we just describe it like we would describe a serial robotic arm? We have a number of rigid links and discrete joints that are kind of describing the structure, and the number of joints, the more joints I basically assume, the more accurately I can represent the shape, but the higher is also the computational expense. So this again makes it kind of like a trade-off in terms of how accurate can I represent my continuous shape and how much parameters or computational complexity do I need to describe it. So throughout the following, we will focus on the variable curvature representation in terms of the shape for the continuum robots. So in our specific case, we can now basically apply this and say we have an arc length that describes each of these tendon-driven robots. And for every point along this arc length, I can define a position and orientation. So I can now establish rod kinematics using this representation. And rod kinematics, usually what they do is they describe how the position and orientation change as I go along the arc length. So it's essentially the rate of change of my shape with respect to the length of the robot. And these differential equations now depend on the orientation itself, but they also depend on these new variables that I introduced. It's V and U. And these variables is what we call strain variables. So they basically tell me what is the local deformation of my robot at every point along its arc length S. And in this specific case, U tells me how much the robot is bending and twisting at this point, and V is telling me how much the robot is sharing and elongating at this point. So both are 3x1 vectors, and it's basically the strain, the mechanical strain of the robot. And by integrating those, I can get the position and orientation. One analogy is, imagine like any rigid body moving in 3D space with respect to time. Then we can say U and V are almost like the velocity of this rigid body. And by integrating this velocity, I get the position orientation of that body. And we're doing kind of like the same with the shape of the robot here, but we're not moving in the time domain, we're moving in the domain of this arc length. And then these are kind of like the velocities or rate of change of these variables along this arc length. So this gives me like an ordinary differential equation for my position and orientation. So this basically tells me how I can kinematically represent the shape of the robot. But that's not everything, because you've seen these robots are very soft and compliant. So we actually need to pay special attention how we model this deformation in terms of material mechanics. And this is where we now look into elasticity theory. And in elasticity theory, there's a specific part for slender one-dimensional structures or rods, exactly what we want. And the most common, or one of the most common theories there is the COSSERAT rod theory. So now, because we are investigating the mechanics, there are like a couple new variables that we need to take into account. One, we have the internal stress of the robot. So at every point S along the robot, we have an internal force and an internal moment. And then we have F and L, which are basically distributed external forces that can act on the robot. That can be anything from interaction forces or gravity due to the weight of the robot itself. And these basically have an influence on how the robot will deform. So using these parameters, I can now write down a couple of equations. So one is I enforce a static equilibrium at every point S along the arc length. So basically just saying the internal stress will balance out with the distributed external forces and moments. And then I can use constitutive laws. It's basically the properties of the material to relate the deformation or the strain of the rod with respect to its internal stress. So in the most simple case, we can often assume a linear constitutive law where we have a simple stiffness matrix that depends on the material of the robot that relates the internal deformation with the internal stress. So this, like more or less is nothing else than like Hooke's law that some of you might be familiar with. So now using these two equations and using the rod kinematics from the previous slide, we can now write a system of differential equations for the whole state of the robot. We have our differential equations for position orientation. And we have now differential equations for the strain variables as well, depending on my external loads L and F, and on the stiffness of the robot, essentially. So this is a set of differential equations that I can solve to get the robot. One important thing to notice here, we have like tendons routed through the robot, which actually reside to these loads deforming the robot. So what we need to do now is we need to express our tendon actuation as distributed loads. So essentially, we will express the force that the tendons will act on the robot throughout these variables F and L. You can do that. I won't go into detail of that, but I cited the publication here if you're interested in all the math. But essentially, you can now derive specific COSSERAT rod equations for tendon-driven continuum robots, where the strain variables have like a new form of differential equations that basically depend on like external forces and also my tendon forces. So these are like a lot of simplifying terms. It's not very important what's written inside of them, so to speak, but these mainly depend on like my tendon actuation. And when I talk about tendon actuation, what I mean is these depend on the tendon tension or force which I pull the tendons down here. So these depend on tau, and for this specific continuum robot, we said we have 4 tendons. So these depend on this 4-dimensional vector tau, telling me what is the tension of each of those tendons. And now I can essentially integrate these differential equations as an initial value problem. So I can integrate them starting here and kind of like iteratively going along my arc length. And I can, by this, recover the shape of my robot. I can recover the whole state along the whole arc length with respect to all of these 4 state variables. However, what I need for this is I need actually the initial values at point s equals 0. And for position orientation, that's rather simple. I mean, I have assembled the robot in 3D space. I know where its initial position orientation is. However, the initial strain variables are unknown. So I already have like some unknown parameters for each of these robots, which is the initial values for u and v. And this is basically a 6x1 vector now. And once I have these variables, I can like integrate these equations to get the full shape. So we can say this is kind of the minimal set of parameters that I need to now recover the whole shape and state of the robot. There's actually one more problem that we often face in these specific robots. I told you that these variables here depend on the tendon force tau, but often these robots are not controlled in terms of a force that I apply to the rod, but rather a absolute displacement. So often I say, oh, I pull the tendon by 1 centimeter and I lock it there, but I don't actively control the tendon tension. So in our case, we will control the length of these tendons and we have no control over the force of these tendons. What that means is that this tendon tension tau that I introduced is actually unknown as well. So for each tendon-driven continuum robot, we now have 10 parameters that are unknown, which are x and tau. And we will can discuss later how we actually recover and solve for these unknown parameters. So just like a very small update of the figure that I showed before, it's basically the same depiction of the robot with all the variables that are in play here for the modeling. Now I can already say, okay, for each robot, I can represent the shape with this minimal set of unknown parameters u and v at s equals 0. And I also introduced now the tendon tension of each robot. Oh, sorry. Give me 1 second, the light turns off from time to time. And let me finish this slide. So this tendon tension I introduced here now, in addition to the actuation, which is the tendon displacement. That means our kind of problem formulation changed very slightly too, because now we also have to solve for this unknown tendon tension. Before I continue, I will just turn on the light real quick. All right. Okay. And essentially what we have now, we have like all the variables that describe the state of the robot. And the thing we need now is we need to derive equations that relate each of these variables with respect to each other. And we can do that by looking at the constraint equations of the parallel system. And there are a couple that we have to consider or essentially enforce. So the very first one is, remember when we talked about, we have a static model. So that means we consider the robot to be in a static equilibrium. So I have to enforce that my sum of forces at moment at this point equals 0. So it's these are 6 equations, 3 for the forces, 3 for the moments, because I'm in 3D space. And these are the first set of constraint equations I have to consider. Then I can look at these coupling joints here that couple each of these robots to the anti-factor platform. Essentially, they enforce like a position constraint, saying that the distal position of each of those robots needs to align with this coupling point. So that is 3 equations per robot because we have position in x, y, z. And then also that the moment in these spherical joints has to be 0 because it's spherical joints, they cannot support any moment. So we need to enforce this as well. So for each joint, these are 6 more equations for each robot. And then we have one more constraint that comes from the tendon actuation. So remember when I said we control the length, the change of length of each tendon. So we, knowing the initial length of the robot and then knowing how much we pulled each tendon, we know basically how long each tendon should be in the structure. And we need to enforce this as a constraint equation, which will then help us to solve for this unknown tendon tension tau. So in total, we have a system of 36 constraint equations. We have 10 per robot plus 6. And these depend on basically all of these variables, explicitly or implicitly, because like tau and x will be used to recover the whole state of each continuum robot. And then this whole state will basically be used to evaluate these constraint equations. So I can write them down as this set of constraint equations that all have to be 0. So we can express them as like equality equations. And this is of size 36. So now what I want to do is basically, I just want to look at these constraint equations and look at the specific problem that I want to solve. So we will start with the forward kinetostatic problem. Remember, our unknowns here are the anti-effector pose, the shape of the robots, and tau. And I can look at the constraint equations and basically see which values are unknown. So our first unknown value is the anti-effector pose. It's an SE3, which means we have 6 free parameters, 3 for position, 3 for orientation. I have 12 unknown tendon forces because each of the 3 robots has 4 tendons. And then for each robot, I have 6 parameters that are representing the shape, which is 18. So in total, we can see we have 12 plus 18 plus 6, 36 unknowns, and we also have 36 equations. It's pretty good. So we have a 36 times 36 system to solve. We can just basically enforce these boundary conditions to solve for the unknowns. We can do the same for the inverse kinetostatics. So the same approach. Now, this time we say we know where the anti-effector pose should be, and we want to know what actuation do I need to actually move the robot there. So now it changes a bit because, as I said before, we have a redundant robot. So our Q is actually element of R to the power of 9. And then we have, again, the unknown tendon tensions and unknown shape. So now we have a 36 times 39 non-square system to solve, which makes sense because, as we discussed, our robot has 9 degrees of freedom actuation, and we only control 6 degrees of freedom for the pose. So there are 3 free parameters in the null space of this robot. So this is also respected here because we have 3 more variables than like equations we actually need to enforce. Okay, I just want to briefly talk about how we now solve these boundary conditions with respect to the unknown values. And we do this by using a so-called shooting method. And the way this works is we start by just taking any initial guess for the unknown parameters. And just to recall, depending on the problem that we consider, these are the unknown parameters that I want to solve for. And then having like this value for the unknown parameters, especially for x and tau, I will basically compute the shape of each of the individual robots by just integrating these ordinary differential equations. After this step, I can then evaluate my constraint equations and can check if they are below some certain threshold. So ideally, I want to solve them for 0. So I solve for like some very low threshold. If that's the case, I have like solved my equations. If that's not the case, what I do is I compute a numerical Jacobian that relates changes of my unknown values to changes in this boundary condition. It's kind of like a gradient, and I can go along this gradient to essentially minimize my constraint equation. So I use this Jacobian that I compute to update my unknown values, and then I loop through this over and over again. We call this shooting method because we're like guessing the unknown values at the start of each robot, and then we are integrating towards the end of each robot. So we kind of say we're like shooting from the start of the robot to the end. And that's like a very well-known method in like solving numerically solving ordinary differential equations. And that's what we apply here to solve this. There's one last thing, like one last theoretical thing that I want to discuss that we can do with the model. And that is linearizing the model around a specific current operating point. So we know that like our constraint equations have to equal to 0. And the same way we can say that any change or any perturbation in the constraint equation also has to equal to 0 because our constraint equations always have to be fulfilled. So I just wrote them down here again. I summarized all my uncontrolled variables, x and tau, into this variable y, u. And this kind of like change of my boundary conditions, I can now take the derivative of my boundary conditions with respect to all of the different parameters that it depends on. So I basically linearize my constraint equation with respect to all of the parameters. So these are all partial derivatives of my constraint equation with respect to all of these individual variables. I just want to slightly note, we're like slightly abusing notation here. This is like a perturbation of the pose. We will not do this as a 4x4 matrix in the Lie group, but we would rather do this in like the corresponding Lie algebra. But for simplicity, we will write it down like this. So what this results to is I can write all of these partial derivatives as matrices that relate changes of specific variables to changes in my constraint equations. So it might not be completely obvious why this is useful, but I now want to convince you that it is useful because looking at this linearization of my constraint equations or of my model equations, I can actually derive Jacobian and compliance matrices describing the kinematic properties of my robot. So I can actually study how this robot behaves now given this. So again, I just like wrote down my linearization here in this equation. And for now, let's consider that the force that's acting on the robot will not change. So I will just set the changes in external loading to 0 for simplicity here. Let's consider the robot is in any state where the force that's acting on him remains the same. So looking at this, I can now rearrange all of these equations essentially to bring my changes in Q on one side and my changes on the anti-factor pose and my unknown variables or uncontrolled variables on the other side. And if we inspect this specific structure, we can see we have now a relation to changes in my actuation to changes in my anti-factor pose. And there's nothing else than my forward Jacobian, and that relates joint velocities to task space velocities. So the upper block of this expression is my Jacobian, and the lower block basically relates changes in my actuation to changes in my uncontrolled variables, which is the shape of each robot and the tensions of these tendons. And I can then basically use the same expression and just do like an inverse mapping. So I can derive an inverse Jacobian by just like rearranging it slightly different, bringing the anti-factor pose on one side and bringing my actuation values on the other side. I can then say, okay, for any desired anti-factor velocity, I would need these actuator velocities. So this is just how we get our like inverse and forward Jacobian. And we can do something very similar by assuming I'm now locking my actuators. So my configuration parameters in terms of the motor actuation is static. And I then rearrange these equations to get like a very similar relationship between changes in the external force to changes in my anti-factor pose. And that's nothing else than the compliance or inverse stiffness of my robot, basically telling me like how much the robot would move if I like push it with like an external force. So these are very, very useful matrices and metrics later when I look at the kinematic properties of my robot. And looking at these specific formulations, we can actually also identify singularities. So we see that here in this case, we actually need to invert this stacked matrix. And if this matrix becomes non-invertible, like we cannot solve this problem anymore, and we have like a singularity in our model. And for this specific case, if we call it like a type 1 singularity, if this matrix becomes singular, it means that there can be changes in my actuation or in my uncontrolled variables that lead to no anti-factor motion. And it's like that's the most typical singularity that most roboticists like know, because it's also apparent in like serial arms. It's just like my anti-factor basically loses 1 degree of freedom and it might not be fully controllable anymore. I can then look at like the other equations that I derived for my forward Jacobian and my compliance matrix, and I can then identify a second type of singularity, which is this. And in this case, that means that there might be some changes in my uncontrolled variables, or there might be some changes in my anti-factor pose, even though my actuators are locked and there's no change in external loading. And essentially, that means that the robot becomes unstable. There's like some motion of the robot shape or anti-factor that's uncontrollable. It's neither a result of actuation or external or like new external forces. So we basically say in this specific state, the robot becomes unstable. And you can see it affects both my Jacobian and compliance metrics. So close to these singularities, both of these will essentially blow up, meaning that even small changes in my actuation or my external force will lead to very large changes in my anti-factor pose. So yeah, we often say this is like an instability of this robot, and this is a very typical singularity that you will also find in conventional parallel robots that often needs to be taken care of to not like operate close to it. Okay, I want to spend like the last couple of minutes just to briefly talk about some analysis that we did of this specific robot. So we first wanted to like evaluate our model with respect to a real robotic prototype to see how accurate it is. So in terms of our robotic system, you can again see we have like the 3 tendon-driven continuum robots. We have the spherical joints and the anti-factor platform, and then each robot is controlled by its own actuation unit. So what we did is we considered a set of 30 different configurations in which we evaluated the robot, and essentially we like measured the pose of the robot with like a laser scanner. And we then had like 30 different poses that were like distributed in the workspace of this robot, from which we used a couple to calibrate our model to. So we then considered the same set of configurations in our simulation to see how good is the agreement of our model with respect to a real robotic system, just to see how valid the equations that we implemented actually are. And the results are shown here, or like summarized here on this slide. So essentially, over all of these 30 configurations, we achieved median position accuracies of 4.9 millimeters and median orientation accuracies of 6.4 degrees. And you can here see this is like just a sample motion that we use to kind of like align the model with our prototype. And you can see that the match is actually quite good, and we are able to depict the motions of this robot quite accurately. So that was pretty good, because now we knew, okay, what we actually implemented depicts the real robotic system. So we can now actually go ahead and use our model in simulation to kind of study the kinematic properties of the system in more detail. So one thing that we did is, using the Jacobian matrix and the compliance matrices that I just derived, basically looked at their singular values and vectors. So we did a singular value decomposition to just see how the singular values and vectors are. And then what you can do is you can plot these manipulability and ellipsoid, manipulability and compliance ellipsoid from the singular value decomposition to look at how well can the robot be positioned and oriented with respect to the actuation, and how stiff is the robot in basically in different directions. So the larger an ellipsoid is in like one specific direction means that I can like easily or like more easily move it in this specific direction with respect to my actuators for the manipulability, or for the compliance means if an ellipsoid is large in one direction, that means the robot can easily be pushed in this direction by an external force. So for compliance, if we want a high stiffness, we would like shoot for low compliance ellipsoids. So these are actually very useful tools now to study different arrangements of these robots, or to just see how they kinematically would behave. And then one last thing that we did is we can now also assess what is the workspace of the robot with respect to its reachable positions. So what you can see here is a 3D plot of all the reachable positions of the robot for one specific anti-factor orientation. And we actually also can look at the occurrence of these type 2 singularities here to see where the robot might become unstable and where we might need to take special care in terms of operating the robot close to these instabilities. So these are just some very useful tools to like investigate the properties of the robot in simulation now. So with that, I'm at the end of my talk. Thanks for your attention. I just want to briefly conclude and summarize what we talked about today. So I hope I could introduce tendon-driven parallel continuum robots to you as like a way to overcome this like challenge of a lack of stiffness in continuum robotic systems. We derived and implemented an accurate kinetostatic model, and I've hopefully shown that we can now use this to actually simulate and study the motions of this robot and the kinematic properties in detail. And right now, my current and future work kind of focuses on using what I've done so far to synthesize and optimize designs, kinematic designs, according to specific kinematic property requirements. I'm looking into how to best coordinate and control the motions of this robot, especially because the robot is redundant. I have like this null space that I can potentially resolve. And then, eventually we want to study these robots in the envisioned application. Well, thanks so much for your attention, and also special thanks to my lab, to my supervisor, Jessica Bodnar-Kars, and of course, all my colleagues who like support me and make doing a PhD a lot more easier. Thanks, guys.
Thanks for the great talk, Sven. Amazing work. Yeah. I think now it's our QA section, and any questions from the audience, please just unmute yourself and ask here. I guess maybe I can start with one question. So, you know, for robotics arms, there are many like famous robotic arm products from the industry, like UR5 and Franca Amica kind of things. Yeah. Is there any such tendon-driven continuum robots from the industry products?
Yeah, that's one of the main challenges we often face. So there are actually no off-the-shelf continuum robots you can buy to just like kickstart kind of your research. So that's like one of the, I want to say disadvantages, but sometimes challenge. Like we implement like a model and want to see how well it works, but we also have to build like the prototype to like double check or anything. So yeah, so a lot of the robots, or like all of the robots we study here, are actually like built by ourselves, by our lab. So we always have like this component of like building our own prototypes. which like takes it takes quite some time to do just like on the side to like verify some algorithms. But of course, at this point we have prototypes now that we of course like we reuse them. But yeah, that's like definitely a challenge in continuum robotics research, I think, especially for fields like computer science that are maybe not as like, I don't know, that might lack skills in terms of mechanical design or engineering. I mean, myself too, I'm an electrical engineer. I'm not the best at like building these robots. So yeah, I can see that this is challenging.
Yeah. But this is also an advantage, right? After you have those prototypes.
Oh yeah, sure. But it would also be nice to just like buy something that just works for you, you know. But
yeah, just type install something.
Yeah.
Oh, I see there's a question from the audience. Please go ahead. Priyanka Rao, right?
Yes. Hi, Sven. Thank you for your presentation. As always, it was really nice listening to your talk. Following up on the previous question, I was wondering, are there any particular challenges that you see that would go into bringing this kind of robot into the market, as in that like a industrial built robot?
Well, that's a very good question. I think like right now it's very hard to pinpoint like a specific set of requirements. I think like every lab that builds like these tendon-driven robot is like slightly different. So I think, yeah, like, I mean, yeah, so it would be nice to have like one generalizing platform that people could just buy. But I think you would need to make sure that the thing you're buying is applicable for all the stuff that people would need, you know, because right now I think we build our prototypes with respect to our needs. So I'm not sure if that's the biggest challenge, but that's just the very first thing that comes to my mind. What if I would need to like build something like this right now? Yeah. And it's also, there's like so much stuff like, do you want to like exchange the tenants at some points? Do you want to like have the actuation unit coupled to the robot? There are like a lot of stuff that would be actually it would be almost like necessary for like to have a product like this. But our prototypes are just like very fundamental in that regard still, if that makes sense.
Yeah, that makes sense. So let's say use the design you have right now with the same exact dimensions. So if it was, let's assume there's a task that perfectly fits this robot.
Okay.
Do you anticipate any like problems? Let's assume someone built it and it's amazing and it works really well, like a mechanical engineer with a good degree who knows what he or she is doing. What happens then? Like, do you anticipate some particular issues to come up? I guess that like zeroing in on my question.
Well, okay, one question would be, does this prototype also come with a model? And if not, then all of the very intrinsic parameters would need to be very accurately stated for researchers to actually work with it. And it's not just like, oh, like joint limits for rigid bodies. We have like, oh, what is the elasticity of the material? What is actually what is the stiffness of a tendon? Because it can potentially also elongate and stuff, right? So I think that might be a problem in calibrating it, because there are like just so many little things, I think.
Yeah, okay, very nice. Thank you.
Good
Really
question.
interesting one.
Yeah.
So there's another question from the audience. Please just go ahead. Yeah.
Hi, Sven. Thanks for the great presentation. I wanted to ask about your models and your equations. How well do you think they scale to larger structures or heavier structures? Like you show diameters like the size of fingers. What if you're working with a continuum parallel robot the size of like a Canadarm, like in space?
Yeah.
I mean, that's like a gravity-less environment, but I guess like if you could speak to some of these points, that'd be cool.
Yeah. So generally the model can just be adapted to like any structure by just adapting the weight of all the components, the material properties and stuff, because right now even like this own weight of the robot is fully modeled. So theoretically, by just adapting these parameters to any new structure should work. But there are some unmodeled effects in here, which is like hysteresis of the material, friction of the tendons, and then depending on the prototype that you investigate, or maybe even of the dimension of the prototype, these might have a bigger effect that might not allow you to like neglect them anymore. So maybe you might need to look into including some of these physical effects that we don't consider right now into your model. But generally, it should be scalable-ish, I think. But like it's always easier to model more lightweight robots, because then the weight and the force has like less impact on like the shape deformation.
Right, and it's all statics. If you work
that's another thing. Like we don't consider any dynamics. So like once you have once you have like more like faster changing actuation or actually suddenly changing external forces, that's also a thing that would need to be taken into account to like move to a full dynamic model and not assume quasi-static motion of this robot.
Cool. Thanks for your answer.
Good question. Thank you.
Yeah,
Any other? Yeah, please.
Yeah, thanks for the great talk. It's really cool. I'm just wondering, like the potential real-world using scenario of the continuum robot. Specifically, I'm wondering the motivation of the 3 parallel continuum robot manipulating a triangular plate. What would be the usage of it in the real world?
No, that is true. So right now our prototype is not necessarily tailored to a specific use case. I think we more constructed it to like verify and check if this kinematic structure generally behaves well, is well conditioned with respect to like the kinematic properties. But like moving more towards the applications, yeah, we would need to like make a smaller like anti-factor platform, for example, with some tool on it. Or ideally, maybe you could even have just like one tip of the rope, like the tip of one of the robots is the whole anti-factor and the other robot just like coupled towards it. And then you can have like a tool at one of those anti-factors of the robots. I think that's a more realistic scenario. Like right now we are still like figuring more like out all the math and theory to make this robot work. And then, yeah, the design would definitely need to be adapted for like a more meaningful application.
I see.
Yeah.
Yeah, thanks.
No, good question. Thank you.
Any other questions? So maybe I can ask another one. So, you know, in robot arms, the like forward kinematics and backward kinematics are basically just some, you know, matrix manipulation, multiplication kind of thing. So it's intuitively it should be very fast, but actually in those real robot experiment in some papers I've read, they often speed up the video by like 4 times or 8 times, otherwise it will be very slow. But in the previous slide, you show that your model can actually run in real time, right? Like 77.
Okay, so one disclaimer here. So the video, that's all real time, but the model is kind of like synced to the video like afterwards. But like essentially this is a sequence of like 1000 quasi-static configurations, and then every like the average computation time for my model here was 78 milliseconds. So then it depends on how you discretize like your path, if it can be real time or not. So let's say this was definitely not real time because I just like used a lot of configurations to like discretize the motion of this video. So you might need to use like a less accurate, I say, like discretization to still like make it real time or like move the robot slower. Yeah, and this is synced like afterwards. So this didn't really like run in parallel. I just moved the robot, did the same motion on this on the model, and then synced them up. Yeah, that's another thing I want to look in next. So right now we just considered specific configuration and checked how well the model can depict them, and we want to actually go to like model-based control using the model to like in real time actually control some more meaningful motion on the robot.
Yeah, I see. Just out of curiosity, are there any works that apply like reinforcement learning to this kind of control or other learning algorithms?
Yeah, so I'm not too much into learning myself, but there are definitely like a lot of like learning algorithms for like control of continuum robots. I haven't seen anything with like the specific parallel continuum robots yet, because this whole like research area is still quite novel, but like machine learning and continuum robots is like a big thing. Just even for like things, just the kinematic mapping, like forward or inverse kinematic, just because there's like all this elasticity theory involved. There's actually another application area that's very, where machine learning can already be applied. Like no one would necessarily learn the kinematics of a serial arm robot because, I mean, it's kind of solved with like matrix multiplication, but for continuum robots, that can make a lot of sense, especially when considering unmodeled effects. Like you can get data from your real robot prototype and then learn on that, and you can get like a way more accurate like thing than you would do with like implementing elasticity theory equations. So that's some stuff that Reinhard actually has done. He has some papers on inverse and forward kinematics learning for one specific type of continuum robot.
I see. That's very interesting. Right. Yeah. Thanks for the answer.
Yeah, no, good question. Thank you.
Yeah. So it's already 30. I think we can just end here. Just one last call. Is there any other questions from the audience? Okay, I think just end here. Let me just stop recording.